Okay, guys, we are back, and we're talking about categorizing electrons inside an atom today. So we're going to talk about inner electrons, which are also called core electrons, outer electrons, and valence electrons. You've probably heard the term valence electrons before, but we're going to refine your definitions. An inner electron or a core electron is an electron in an atom's electron configuration that is common with the previous noble gas. Okay, the noble gases are the elements in the very last column on the periodic table. So it's the column headed by helium. So helium, neon, argon, krypton, xenon, radon, and whatever that bottom one is. Okay, so inner electrons are not involved in bonding. Any completed D subshell or F subshell also become part of the inner or core electrons. D electrons are not core if the D subshell is not full. Only when the D subshell or the F subshell is full does it become part of the core. Outer electrons are those found in the largest shell for the atom, having the highest N value. Valence electrons are those electrons involved in forming compounds. For main group elements, the outer electrons are always your valence electrons. For transition metals, outer electrons as well as uncompleted D or F subshell electrons are considered valence. So valence electrons for main group elements are the same as the outer electrons, but for transition and intertransition metals, outer electrons plus any electrons in a incomplete or incomplete D or F subshell act as valence electrons. Now let's look at some elements and let's look at identifying their inner, outer, and valence. Okay, here's the element silicon. Silicon is a main group element. It's in the P block. I can tell you that because look, its electron configuration ends in a 3p2. So if I looked at the the valence electron, those in the outermost shell, the highest N value, those are valence electrons. Here are my core electrons. Okay, the electron configuration here, 1s2, 2s2. That is the same electron configuration as the element neon. So, electron configuration of neon, core, okay, valence electrons. Let's look at another example. I think I have another one embedded in here. Okay, here's germanium. Germanium is, again, another main group element. So there's what it has in common with the noble gas that ends the row before it. And the D subshell is full, so it becomes part of the core. The 4s and the 4p, those are our valence electrons. Now let me show you some transition metals because they didn't have any good images of transition metals for me to embed in the notes. So let's look at some transition metals. Okay. Now let's look at, let's say, iron, and let's look at yttrium. Iron, okay, has 26 electrons. So we start out 1s2, 2s2, 2p6, 3s2, 3p6, okay, 4s2, and then after 4s in energy comes 3d, and iron is 1, 2, 3, 4, 5, 6 over. So 3d6. Now, the row above iron ends in argon. The electron configuration of argon is 1s2, 2s2, 2p6, 3s2, 3p6. Argon has 18 electrons. So if I look for the electron configuration of argon embedded in iron, okay, this is it. This is what iron has in common with argon. These are core, or we could call them inner electrons. Okay? When I come out here to the end, I know 4s is definitely valence because it's an outer electron. Outer electrons. Okay, so I've got my core, I've got my outer. Now we want to know valence. Well, iron is in the D block. And if I look at the D subshell, it's not full. So those 3D electrons are considered valence. So all of this is valence. So iron has 2 outer electrons, but it's got 8 valence electrons. Okay? So you want to pay attention to that. Outer electrons versus valence electrons. There is a difference if you're not dealing with a main group element. Pay attention to transition and intertransitions. Now, when we look at an electron configuration of an element, it's this stuff at the end that's involved in bonding. Core electrons are never involved in bonding. So we're going to look at a condensed electron configuration that allows us to concentrate in on the electrons that are going to be involved in bonding. Now, when I look at a condensed electron configuration, and I'm going to show you here with iron, okay, what I've boxed in here is what it has common with argon. So I'm going to put argon in brackets, and then I'm just going to add what comes past that. 4s2, 3d6. This is referred to as a condensed electron configuration. In a condensed electron configuration, we write the element that ends the row above, the element we're doing the electron configuration for, okay? And then we add on what comes beyond that. So I'm going to show you some condensed electron configurations. Okay, so we're going to do condensed electron configurations, let's say, for silicon and arsenic and rubidium. So silicon has 14 electrons. Okay? And silicon is on the 3rd row. The row up above it is neon. Now, if we walk across the periodic table, then on the 3rd row, we have 3s2. And then we move on to 3p. And silicon is 2 steps over, so it's 3p2. So neon had 10 electrons, and then 4 more, 14. Okay? If we look at, let's say, barium. Barium has 56 electrons. The row above barium ends in xenon. So I put xenon in the box. Xenon has 54 electrons. Barium is 2 past. Barium is on row 6. So 6s2. So it's very obvious. Okay? If I look at something in the transition metals, let's say we looked at vanadium. Vanadium. Vanadium has 23 electrons. The row above vanadium ends in argon. Argon has 18 electrons. Now, vanadium is on row 4. So 4s2, okay, that brings me to 20. And after 4s is 3d, and it's going to have 3. 4s2, 3d3. If you count over, vanadium is 3 in the D block. Now let's look at this. This is our core. Okay? These are our outer. And there's our valence. If you look at barium up here, again, there's our core. Okay? There's our outer. And our outer are also our valence. On a test in face-to-face, okay, if I ask for an electron configuration, you could do it in this condensed form, you could do it in the long-term electron configuration, you could do a box diagram. They're all perfectly valid. Okay? Now, all atoms, so that's how we do a condensed electron configuration. All right, let's look at the periodic table one more time and kind of talk about some things, reinforce some stuff. That's about the right spot. Okay, let's look at this periodic table. Yep, looks good. Now, remember I talked to you about metals, nonmetals, and metalloids. Here's a periodic table that shows it. So we got the nonmetals here, the metalloids along the stair step, the metals over here. Okay, so main group, transition, intertransition. Couple of things I want to remind you about when we're looking at these guys is that a lot of these are gases. They're insulators. They don't conduct. In the solid phase, they're brittle and they're dull. Okay, metals are solids at room temperature, everything but mercury. They have high boiling points, high melting points. They have a tendency to be shiny. They conduct electricity. They conduct heat, and they're workable. And the metalloids have those kind of wispy in the middle properties. These 6 columns and these 2 columns are our main group elements. D block here in the middle, which are the transition metals. The F block here, intertransition. Notice that for an element, the highest shell value you will find in the electron configuration corresponds to the row that it's on. Okay, and remember at the end of the D block elements, the D subshell is always 1 row behind, F subshells are always 2 rows behind. All right, now. It's time to talk about the properties of the elements. Okay? Turns out that the properties of the elements depend on a repeating pattern of valence electrons and the atomic number. That's why the periodic table is laid out the way that it does. Things that are in columns on the periodic table are called families because they have similar chemical and physical properties. Okay? And going across a row, we call a row on the periodic table a period because the properties change periodically as we go across the period. So let's talk about how the properties depend on this repeating pattern of valence electrons. The first property that we want to talk about is atomic size, the radius of the atom. Now, I want you to understand that the outer edges of an atom are kind of fuzzy. And we measure atomic radii by looking at the distance between two identical atoms. In the metals, it's in a solid crystalline metal sample, and we split it in half to get the radius. For non-metals, we look at two non-metal atoms that are bonded to each other, and we split the difference in half. Not perfect, but it's the best we can do. So as we're going down a family, as the N value increases, so if I go from the first shell, the second shell, third shell, fourth shell, the atomic radii increase. So going down a family, okay, as we go down a family, the atoms get larger. So that means that a lithium atom is bigger than a hydrogen atom, that a sodium atom is bigger than a lithium atom. As we go across a row from left to right, as we would read, we see a decrease in size because the effective nuclear charge goes up. Now guys, let's think about this. As we're going across a row on the periodic table, let me pull up some numbers here for you, an example. Here's showing size. As we go across a row, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Notice that the size is going down. The nucleus is getting bigger as we go from lithium to beryllium to boron to carbon to nitrogen. So the charge in the nucleus is getting bigger. And the electrons we're putting in are all going into the same shell. Okay? Because they're all going into the same shell, there is less shielding. There is some shielding, but there's less shielding, and the attraction each electron feels from the nucleus is actually going up. If the attraction it feels from the nucleus is going up, it gets smaller. So notice, going down a family, atoms get larger. Going from left to right across the periodic table, we see a decreasing atomic radii. I want you to notice here in the D block how we don't change a whole lot. We kind of go down and we kind of even up, and it stays fairly constant. The reason that these stay fairly constant going across a row in the D block is because we're putting electrons into not the outermost shell, but one shell down. Okay? And so for every proton you add to the nucleus, you've added an electron in between the outer electrons and the nucleus, so that almost balances out. Okay, so trends for atomic size. Now the next thing we're going to talk about is ionization energy. Ionization energy is related to the electrostatic forces that hold the particles together. Okay, so ionization energy is going to depend on electrostatic forces. Now don't panic, I'm not going to have you do a calculation with this, but the force between two charged particles is equal to a constant T times the size of the two charges divided by their radius squared. So if the size of the charges go up, it gets harder to pull them apart if they're attracted to each other, harder to push them together if they're repelled by each other. And it also depends on the distance between them, r squared. The further an electron is from the nucleus, on average, the easier it's going to be to pull that electron away, because the attractive force between the nucleus and the electron is going to be less. So outer electrons, okay, because of effective nuclear charge, the bigger an atom gets, usually the easier it's going to be to pull off an electron. Okay? So let's talk about ionization energy. Ionization energy, given the symbol IE, is measured in kilojoules. KJ stands for kilojoules. And this is the energy needed to completely remove 1 mole of electrons from 1 mole of gaseous atoms or ions. Do not worry about what a mole is. Remember, it's just a number like a dozen. Okay? When we remove an electron from an atom, it requires energy. The process is endothermic, so delta H is positive. If we write out the process generically in symbols, we say we have a gaseous atom here, and we're going to go to a gaseous 1 plus ion plus 1 electron. Okay? As we go down a family, ionization energy gets smaller because the atoms are larger and those outer electrons are traveling on average further away from the nucleus and don't feel as great an attraction to the nucleus. So as we go down, it gets easier to remove an electron. So it's easier to remove an electron from potassium than it is to remove an electron from lithium. Okay? As we go left to right on the periodic table, we would expect the ionization energy to go up because those atoms are smaller, those outer electrons are in closer to the nucleus, they're having a stronger interaction with the nucleus, and we have a stronger pull, a larger force we have to overcome to remove the electron. Okay, so let's look at a pretty chart. Now, when we're talking about first ionization energies, we usually concentrate in on the main group elements, the first 2 columns and the last 6. So notice the D block is missing here. So notice as we go down, it becomes easier. As we go down a family, each family as we go down, it gets easier. As we go from left to right, it gets harder. Now, there are a couple of things I want to point out to you. Notice that nitrogen, it goes 1086, that it goes 1402 and down to 1314. Nitrogen has a half-filled subshell. So each of the p orbitals has 1 electron. Turns out nature likes that. That's added stability because it reduces some of the electron repulsion. So it's particularly stable, and the electrons are in just a little bit closer to the nucleus than they are in oxygen. Okay, so there's a little bobble in the trend here. There's a little bobble here too, little bobble, and then as the atoms get bigger, it kind of goes away. Also notice when I go from beryllium to boron, the ionization energy went down. And you'll see it happening as I go from magnesium to aluminum, calcium to gallium, strontium to indium, barium to tellurium. And that's because this family, the beryllium family, the elements in here, okay, have a filled s subshell. When I move over to boron, aluminum, gallium, indium, okay, we see this drop because we've opened up the p subshell. Full subshells are very stable. Half-filled subshells are stable. Anything in between is less stable, and it's easier to remove electrons from. So we see a decrease as we go down a family, and we see a general increase as we go from left to right in ionization energy. Okay? In some situations, when we're creating some ions, we actually want to remove more than one electron. To take the second electron off an atom, it gets increasingly harder. Okay? So here's a table of energy values for removing the first electron, the second electron, all the way up through 7 electrons. Okay? Notice that for sodium, when I remove the first electron, it's 496 kilojoules per mole. But if I try to remove a second one, it's 4,560. And the reason being is sodium only has 1 electron in its outermost shell. To remove a second electron, I've got to remove one from what used to be the core. And that's a whole lot closer into the nucleus. So it's much harder to do. Magnesium has 2 valence electrons. You can see the second electron was more expensive than the first, but that third one's ridiculously expensive. Aluminum has 3, and you can see how it goes up. And when I get to the fourth one, which is in the core, skyrockets. So you can see every successive electron gets harder. And when you move from the outer electrons, the valence electrons, in toward core electrons, it just gets ridiculously hard. So the more electrons you remove, the harder it gets, the more expensive energetically it is to remove those electrons. Every successive electron is harder. Our next trend on the periodic table to look at is electron affinity. Okay? Electron affinity is the energy change in kilojoules accompanying the addition of 1 mole electrons to 1 mole of gaseous atoms or ions. So if it's an atom, 1 mole of gaseous atoms takes in 1 electron to give us 1 mole of gaseous ions with a 1+ charge. Delta H here is usually negative. Okay? In most cases, when an atom takes in an electron, it gives off energy. It's exothermic. The larger the negative value, the better the electron affinity. A positive value for delta H would indicate a poor electronic affinity because the process would be endothermic. You have to force the atom to take the electron. You've got to pump in energy to make it happen. The more positive the value becomes, the poorer the electronic affinity. So, the trend for electron affinities for main group elements isn't quite as pretty as the ionization energy trend. Okay, so let's look at it. So here it is for the main group elements. We can see that if I look at the hydrogen family, as I go up, electron affinity increases. So electron affinity usually increases as we go up a family. Also notice that electron affinity increases as we go left to right. Now, there are some things to pay attention to. Nitrogen has a 0 electron affinity, which means nitrogen is really happy with its half-filled p subshell, doesn't want to pick up any more electrons. Okay? Beryllium, magnesium don't want to pick up any more electrons. They're pretty small orbitals, and the s orbital there is filled. It's not real good at it. Notice that calcium says, I'll take an electron if you really make me, and I'll pay you really cheap for it. But notice that it's kind of out of whack with the general trend. But in general, we can say going up a family, we have an increase in electron affinity. Going from left to right on the periodic table, we should have an electron affinity increase. So guys, this starts telling us some things about the atoms that we can kind of file back in our brains. Namely, elements that are in the lower left-hand corner of the metals, okay, down where francium, cesium, barium, radium are, down in this area. These are going to be larger atoms, okay? They're going to have a tendency to have low ionization energies, so they're easy to remove electrons from, okay? And poor electron affinities, and you don't really want to take in extra electrons. Things up here at the other end, where fluorine, oxygen, chlorine, sulfur are, these atoms have a tendency to be small. They have high ionization energies, they hold on to their own electrons very tightly, and they have good electron affinities, large negative values here, which means they pay pretty well for extra electrons. They want extra electrons. So you can start to see a dichotomy, a difference between the metals and the nonmetals. Metals have a tendency to be larger, to have a looser hold on their outer electrons, and they don't really want to buy extra electrons. Nonmetals have a tendency to be small atoms that have a very good grip on their own electrons, and on top of that, they want to buy extra electrons. Okay, so we can start to see differences in the behaviors between the two sides of the periodic table. Now, the last characteristic I'm going to mention is one that I'm not really super fond of, but that's okay. It's metallic character. We say that metallic character increases as we go down a family, and it increases right to left on the periodic table. Now, this makes good sense, guys, because to the left and down, that's where our metals are, and to the right and up, that's where our nonmetals are. Okay? And if you look at something like the nitrogen family, you can see as you go down the family, you go nonmetal, nonmetal, metalloid, metalloid, metal, metal. So you can see going down a family, you have more metallic characteristics. Now it's time to talk about ion formation. Okay? Monatomic ions. Mono means one. So a monatomic ion is an ion made out of a single atom. Okay? The number of protons does not equal the number of electrons. So remember, in a cation, like I said earlier, number of protons is greater than the number of electrons, so we're going to have positive charge. We create that by losing electrons. Anions are negatively charged because the number of electrons is greater than the number of protons. We're going to form anions by an atom taking in electrons. Okay? To indicate ions, we're going to use superscripts behind the symbol of the element. So if I had Li with a 1 plus behind it, that means I have a lithium atom that has given up one electron and it's become positively charged. It's a cation. Oxygen 2 minus means that I have an oxygen atom that took in 2 electrons, so I now have 2 more electrons than I do protons, and it's negatively 2 charged. One of the things that's important here is notice that the plus and minus is written behind the number. It's 1 plus, 2 minus. Okay? Now, there are trends on the periodic table. The trends on the periodic table for ionization energy and electron affinity help point us in the right direction as to what kind of ion a specific kind of element is going to form. Okay? To form cations, positively charged ions, we want to build them out of atoms where the electrons are cheap, where the electrons are easier to remove. And that's going to be on the metal side of the periodic table. So metals have a tendency to form cations because their electrons are not that expensive. Okay? So cations are going to be formed from metal atoms. Nonmetals don't make good cations because remember they have a very strong grip on their electrons and their electrons are very expensive. So let's concentrate in on metals for a minute and look at cation formation, and then we're going to go to nonmetals and we're going to look at anion formation. Okay? Now, as they were trying to figure out about what kind of predictions they could make about what kind of ion something would form, they used as their guide the transition metals. I mean, not the transition metals, the noble gases. Noble gases or inert gases don't get involved in bonding. And if we look at their electron configuration, we start to see something that's particularly unique to them. Now I'm going to write some electron configurations of our noble gases here. Okay, let's scoot over. Okay, if we start off with helium, He, its electron configuration is 1s2. The outermost shell for helium is filled because its outermost shell is the first shell that only has the s subshell. If we go on to neon, it's 1s2, 2s2, 2p6. The outermost shell has a complete s and p subshell. Argon, 1s2, 2s2, 2p6, 3s2, 3p6. The outermost shell has 8 electrons in it in the s and p subshell. If we go on to one below, and I'll go to krypton, and I'm going to be lazy and use the abbreviated condensed form, it's argon, 4s2, 3d10, 4p6. The outermost shell has 8 electrons in it. All the members of the noble gas family have 8 electrons in their outermost shell. So what we see when we start looking at ion formation, especially for main group elements, is they want to look like their nearest noble gas neighbor. Okay? So if I looked at lithium, a lithium's electron configuration 1s2, 2s1. A lithium has 1 electron more than helium. If lithium wants to look like helium, it's going to need to give up this 1 electron. Okay? So I get a lithium 1 plus ion, 1s2. It gets to look like helium. In the same family with lithium, down below it, we find neon. Oh, excuse me, no, neon. We find, under lithium, we find sodium. Okay? Sodium's electron configuration is 1s2, 2s2, 2p6, 3s1. Again, it's 1 electron past neon. So sodium, like lithium, wants to form a 1 plus ion. 1s2, 2s2, 2p6. So that it now looks like neon. This is referred to as being isoelectric. Isoelectric means having the same electron configuration. And other elements on the periodic table want to masquerade as a noble gas. So let me pull up a pretty little table here, and we'll look at it. Come on, computer, work with me. Okay, so if we scoot over here, okay, lithium, sodium, potassium, rubidium, magnesium, calcium, strontium, they're going to want to lose electrons to look like their nearest noble gas neighbor. We've just seen that lithium, sodium, potassium, rubidium, cesium all are going to lose 1 because they're 1 electron past their nearest noble gas neighbor in electron configuration. Magnesium, calcium, strontium, barium, we can see are 2. They're going to want to lose 2 electrons to look like their nearest noble gas neighbor. Okay? So everybody in the first family on the periodic table, they're going to lose 1 electron. The next one, going to lose 2. Okay? So if we look at sodium, lithium, potassium, rubidium, cesium, the members of the first family, which by the way are called alkali metals, common name, they are all going to form +1 ions. The next column over, headed by beryllium, which are called the alkaline earth metals, will form 2+ ions. And aluminum is going to form a 3+ ion. Okay, because it's on the 3rd row, no D block. Okay, so here's kind of an interesting look at the periodic table, kind of putting it on a drum and putting the noble gases in the middle. Lithium, sodium, potassium, rubidium, cesium form 1+ ions, or you can just put the plus. Magnesium, calcium, strontium, barium always form 2+. Aluminum always forms a 3+. Okay? And that's because of how far off they are from their nearest noble gas neighbor. Now let's talk about transition metals. We think about transition metals trying to look like a nearest noble gas neighbor. For most of them, it's almost impossible. Something like scandium and yttrium can do it, but something like iron can't. Okay? So, how does a transition metal form a cation? For all transition metals, the first electrons they lose on their way to becoming a pseudo-noble gas, okay, a false noble gas, is the electrons in their outermost shell. That in the highest N value, so they lose their S electrons in their outermost shell first, before they lose any D electrons. Okay? So we're going to look at some transition metals here. Now, let's look at this chart. Okay? Right here, this dotted line, that's the 4th period. So 4s is more stable. But notice when I get over to here where the 3D comes in, we start to, with scandium, see that 3D is more stable than 4s. So that the s electrons are going to be removed before the d electrons. Now, let's look at iron as kind of a poster child here. Iron has a tendency to form 2 ions. A 2+ ion where it loses 2 electrons, and a 3+ ion where it loses 3 electrons. So let's look at these electron configurations. So if we look at iron, Fe, the row that ends above it is argon. So its electron configuration is argon, 4s2, 3d6. Okay? When iron forms a 2+ ion, the first electrons it loses is its 4s. So it becomes argon 3d6. When iron forms an iron 3+, it now loses one of those 3d electrons and becomes argon 3d5. Now, 3d5 is important. That's a half-filled subshell. Nature likes half-filled subshells. So an iron 3+ ion is more favorable actually than an iron 2+ in that it has an electron configuration where there's a less electron-electron repulsion in the D subshell. Okay? If we looked at something like, scandium. We would have argon, 4s2, 3d1. Well, scandium can actually form a 3+ ion and lose all of those electrons and have an electron configuration identical with argon. Scandium is one of the few transition metals that can get itself to look exactly like a noble gas. Okay? But different transition metals are going to have different charge states. Now I also want to show you zinc. Zinc's electron configuration is argon, 4s2, 3d10. The D subshell is full. Half-filled subshells and complete subshells are very stable. Zinc only forms a zinc +2 ion, and its electron configuration becomes argon 3d10. We lost the outermost electrons first. This is referred to as a pseudo noble gas configuration. My pseudo-noble gas configuration is a noble gas configuration plus a completed D shell. Okay? So that's a pseudo-noble gas configuration. Now, let's talk about what are referred to as poor metals. Poor metals are the metals underneath the stair step. Okay? So it's things like tin and indium and lead. They're noble gases. They are poor gases. If we look at tin, tin is on the 5th row. The row above it ends in krypton. So I've got krypton, 5s2, 4d10, 5p, and it's 1, 2 over in the P block, 5p2. Okay? Now, we always lose electrons in our outermost shell first. Tin can form a tin 2+ ion, krypton, 5s2, 4d10, and the 5p2 have been lost. We emptied out the P subshell. Tin can also form a 4+ ion, which is krypton, 4d10. We lost the 5s electrons. Okay? Tin 4 ion. Tin 4+ ion. And this again is a pseudo-noble gas configuration. Okay? So for the transition metals and the poor metals, there can be oftentimes more than one charge state. They lose as many electrons as they can under the energy restrictions that they can, trying to look as much like a noble gas as possible. But for most of them, achieving a noble gas configuration is not going to happen. Okay? So we have metals that are going to form cations. Now let's talk about anion formation. As we're thinking about anion formation, anions are normally made from nonmetals. Anions are formed by picking up electrons to try to look like your nearest noble gas neighbor. So we're going to look at fluorine, oxygen, and nitrogen as our poster child. Okay? If I look at nitrogen, oxygen, fluorine, their nearest global gas neighbor is neon. Neon is 1s2, 2s2, 2p6. Nitrogen is 1s2, 2s2, 2p5. Oxygen is 1s2, 2s, no it's not 5, it's 3. 1s2, 2s2, 2p4. And fluorine is 1s2, 2s2, 2p5. Now if I look at these and I look at the p subshell compared to neon for each of these, fluorine is 1 electron away from looking like neon. So fluorine is going to form a 1- ion. It's going to pick up an electron, become 1s2, 2s2, 2p6. It now looks like neon. Oxygen is 2 away. So oxygen wants to find a 2- ion, 1s2, 2s2, 2p6. Nitrogen is going to want to pick up 3. Nitrogen is going to form a 3- ion, 1s2, 2s2, 2p6. So oxygen, a nitrogen 3- ion, an oxygen 2- ion, and a fluoride 1- ion are all isoelectric with neon. They all have the same electron configuration. So let's look at this drum again. Okay, so if we look here, that means that sulfur 2-, chlorine 1-, argon, potassium 1+, and calcium 2+ are all isoelectric. They all have the electron configuration of argon. Nitrogen 3-, oxygen 2-, fluorine 1-, neon, sodium 1+, magnesium 2+, and aluminum 3+ are all isoelectric. So the things on these rows are isoelectric with each other, which means they have the same electron configuration, because everybody wants to look like a noble gas. Now, I want to mention carbon for a second, okay? If you look at the electron configuration of carbon, 1s2, 2s2, 2p2. Carbon is 4 electrons away from looking like neon, and it's 4 electrons away from looking like helium. Carbon doesn't like to form ions. 4 electrons for such a small atom with so few electrons is really hard to do. So carbon has a tendency not to form ions at all. Boron is only 3 electrons plus past helium, but again, it's a very small atom and it's 3 away. Getting boron to form an ion is pretty hard. If it forms an ion, it's going to form a 3+ ion, but it's not very likely. Okay? All right, how we doing on time? We're almost, I got like 7 minutes here before I'm going to end this lecture. So we're going to talk about naming monatomic ions. Our naming of monatomic ions is based on the name of the element that we're making the ion from. So let's start by naming cations. Now, the name of the cation for the first 2 columns on the periodic table, the alkali metals and the alkali earth metals, are really easy. All we have to do is take the name of the metal and tap the word ion on it. Because looking at the periodic table, we're supposed to be able to decide what the charge is. The first column on the periodic table, the one that's headed by hydrogen, so it's hydrogen, lithium, sodium, potassium. Ignoring hydrogen, starting with lithium on down, they always form 1+ ions. The next column over, headed by beryllium, they always form 2+ ions. So if I just tell you I have the ion, you're supposed to be able to know what the name is. So if we had Sodium 1+ is just called the sodium ion. Calcium 1+ is just 2+ is called the calcium ion. Barium 2+ would just be called the barium ion. Now, there are some other metals, okay, that when they form ions, we just say the name of the metal and the ion. Silver is always just the silver ion, and silver is always 1+. Zinc only forms a 2+ ion, so it's always just the zinc ion. And aluminum always forms a 3+ ion, so it's just called the aluminum ion. Okay? So if you look at this handy dandy chart, okay, there's our alkali metals and silver at 1+, the alkaline earth metals at 2+, and notice aluminum there at 3+. The name of the ion is just the name of the metal, and you tack the word ion on it. Okay? We'll come back to this chart when we're talking about anions. For transition metals and poor metals, the transition metals, the metals underneath the stair step, most of them can have more than one charge state. So we've got to include the charge in the name. So it's going to be the name of the metal, Roman numeral with the charge, and then the word ion. So Fe2+ is iron 2 ion. Fe3+ is iron 3 ion. Okay? Now, some metals only have one charge state, transition metals. Silver and zinc. Silver is always 1+, zinc is always 2+. So you got to remember those. It's just silver ion, zinc ion. I'm not going to worry so much about cadmium, strontium, and yttrium, but they're, again, they fall in that category. Aluminum is the only poor metal that only has one charge state, so its name doesn't include its charge. Okay, so I'm going to write some metal ions over here, and we're going to name them. So, all right, let's start down here at the bottom. Mn, that's manganese. Okay? Manganese is a transition metal. It's in the D block. So I know I'm going to have to put a Roman numeral here for its charge, and then the word ion. So we call this the manganese 3 ion. Copper, Cu. Copper is a transition metal. So I'm going to have to include a Roman numeral for its charge, copper 1 ion. Okay. Magnesium is a main group element. It's in the second column. So I'm just going to say magnesium ion. And aluminum is a poor metal, but it only has one charge state. So that's called the aluminum ion. Okay? Now it takes practice, but you can do it.